Hi, this is Synthchaser from synthchaser.com. Today we're going to troubleshoot and repair this dead Juno 106. I think this is the first Juno 106 video I'm doing, and people ask me if I even work on these, because considering how common these synths are, they've been noticeably absent from my channel. Yes, I do work on the Juno 106, but I rarely come across any with problems interesting enough to make a video about. The main thing is usually voice chip repair, replacement, and calibration, and I'd imagine there's a bunch of good videos on that already. But this one may be an interesting fix that could help one or two people out there and possibly entertain one or two more. So I got this unfinished Juno 106 in a few pieces from another tech. Side panels are missing, but I'll deal with that later. Voice chips were already replaced, so that's helpful. All the boards were disconnected. The power inlet had been replaced with an IEC inlet, but had never been permanently wired up, and the transformer was disconnected. So I finished that, powered the synth with all the boards still disconnected from the power supply, tested the different power rails without any load. And they looked good, so I hooked up the other boards. And that brings us to where we are now. When I turn on the synth, sometimes the display flickers, sometimes it just reads 8, and its synth is basically unresponsive. So the goal for this video will be to get the Juno 106 booting up and responsive. I have a pretty good idea what the problem may be, so this may not take a long time to sort out. So in a situation like this where we have a CPU-controlled synth that powers up but's completely unresponsive, a logical first place to look is the CPU. Is this CPU even running? And if not, why? On this channel we've repaired quite a few non-functioning synths and drum machines that were dead due to the CPU not running. You'll notice how I say the CPU not running instead of the CPU being dead. That's because every microprocessor needs at least one thing, and usually more, provided from external sources. The first thing that all microprocessors need to run is power. And I had tested all the rails of the power supply with all the boards disconnected. So I measured all the different power rails here on these headers with these disconnected. But let's test them again now that I've connected a load. Specifically, let's test the digital power rails going to the CPU board, which is this board here. So the power comes in on this connector here, pins 53 to 60, and I'm going to measure the power rails with my oscilloscope. So because the Juno 106 power supply ground isn't tied to earth ground, I'll need to ground my scope probe. That's this little clip here, and I'm extending it with this alligator clip. There's a couple test points on the board labeled D ground here and A ground here for the digital and analog grounds. So I'm going to connect this to the D ground test point. So my probe is now grounded to digital ground, and we're going to check the 5-volt digital rail, which comes in on pins 57 and 58. So this is 53, 54, 55, 56. 57 is this orange wire. And you can see on the oscilloscope it's at 5 volts per division. And so we have about 5 volts there. So it looks okay. There's the 9-volt digital rail, which is on pin 55. So I'll jump back down here. This purple wire. And it's measuring about 12.8 volts, and that's fine. It's just an unregulated voltage that's used to drive the LEDs, so that wouldn't factor into our little problem that we're working on. Okay, so the power coming to this board is good. Now let's make sure that power is actually getting to the CPU chip. This funky looking little chip with the 2 rows of legs on each side is an NEC 7811 processor. There's one here on the CPU board, which we're going to call the main CPU, and then there's another one here on the voice board, or the module board, which we'll call the module board CPU. The service manual calls them something else, which at the time of filming this video in 2022 has become frowned upon terminology. So the pins look weird, but the numbering's the same as a normal DIP package. You start here at pin 1, and then go 2, 3, 4, 5, and they've even put little arrows to kind of help you out as you work your way down. So down the right side of the chip, you go down to 30, 31, 32, and then over to 33, 34, 35, all the way back up to 64. It's a 64-pin chip. Okay, so pin 64, still at 5 volts per division, that's 5 volts. Pin 63, also 5 volts. So yes, the 5 volts is getting the CPU, so it has the power that it needs. But most microprocessors need more than just power to run, though. There's usually a pin called the reset pin that needs to be set for the processor to run. On the data sheet of a chip, you'll see it is called reset with a line over it. That line indicates a logical NOT. So for the processor to be running, we want it to be not reset. So that pin should be a logic true or high, which on 5 volt logic is 5 volts. So the reason the processor can't just start running as soon as it gets power is because all the other components in the system may not be ready to go yet. So a reset circuit, even as simple as just charging up a capacitor through a resistor, gives a little bit of time for power to get stable to the other parts of the system before the processor starts running. So on the 7811, the reset pin is on pin 28. So what I'll do is I'll power off the synthesizer, and I'll get my probe on pin 28. 25, 26, 27, 28. Now I'll turn it on, and we should see that jump up to 5 volts. Yeah, very little delay. It doesn't need to be a long delay, but it does go from 0 volts to 5 volts. So the reset line is good. Another thing the processor needs is a clock signal, so it will execute instructions. I'm not talking about a clock that tells time, just a steady square wave that synchronizes the internal parts of the processor and the processor's interaction with outside components. So clock is usually measured in megahertz. So those of you who dabble in embedded development may be spoiled by today's microcontrollers, which let you configure the speed of an internal clock. But things weren't so evolved back in the 70s and 80s. Many microprocessors, the 7811 included, had most of the clock on board, but still required an external crystal to be connected for the clock to work. And you can see the crystal is, my probe just came off, but the crystal is right here, X1, and this particular crystal is a 12 megahertz crystal. So the crystal on the 106 is connected across pins 30 and 31 of the CPU. So here I'll go ahead and probe pin 30. And you saw that line there on the scope got thicker. Let's gotta keep that on that pin of the chip. Let's do this. So we see that there's some oscillations there. Frequency about 12 megahertz. So, but you'll notice that it's like not a nice clean square wave from 0 to 5 volts. And that's because this isn't the actual clock signal itself. This is just what's happening on the pins of the crystal that the CPU is using to generate the clock. But some sign of activity here is a good indicator that the crystal is okay. So we've checked the things that the processor needs to run. How can we see if the processor is actually running? So we could look for activity on the data bus, but what would that tell us? Not much, since the data bus is where other parts of the system write their data to. We could look for activity on the address bus, or we could do one better and look at another special line that this processor offers, the ALE line. This stands for Address Latch Enable. This line is going to pulse every time the CPU latches an address on its address bus. If the CPU is running, we should see regular activity on that line. It won't be the same rate as the internal clock, and it may not be at a fixed frequency because some instructions will take more clock cycles than others, but there should be at least some sign of life there. I remember that we used this line a few years back to identify a dead 8048 processor on an ARP Quadra. So the ALE line is on pin 46 of this processor, so the little arrow here says pin 45, and I'll go one further, and we have 5 volts, and this is my trigger level. So if I switch to normal triggering, if that were to cross my trigger threshold, it would freeze the display on the scope. but nothing's happening, so that means it's not crossing my trigger threshold. So there's no activity on this line at all. So we can confirm that there's no activity by probing another pin on this processor called the mode 1 pin. The way this pin is currently configured, the processor should also be pulling this line low each time it fetches an opcode to execute. So mode 1 is on pin 27, so 25, 26, 27. And again, that line is high with no sign of activity on this one. So at this point, it's safe to say that we've confirmed that we've got a non-running CPU, and that the problem is with the processor, not any of its support components. But we have a bit of a problem here. And the problem is that this 7811 processor is a mask ROM processor. So that is, it's a processor that has onboard firmware code in ROM that was programmed at the time the chip was manufactured. So you can't just grab another 7811 processor or even another chip from the same family and toss it in there and expect it to work, because it's going to be missing the program code that's in ROM that the synthesizer needs to run. Fortunately, Roland didn't always use the mask ROM version of this CPU, so you notice this open, unpopulated spot on the board labeled 2764. On early Juno 106s, they used a 7810 processor, which is from the same family but doesn't have the onboard ROM. So the program code was stored in an external EEPROM chip that was populated in this spot. So to fix this, we're going to need to get a plain vanilla 7810 processor, burn and install an EEPROM with the firmware code, and make a couple of changes on the board so the processor knows to look for the external ROM instead of the internal one. So let's take this board out and make those changes. So here's the processor board, and this is the chip that we're going to be replacing. And on the back side of the board, I can see it, there is a thick layer of flux residues left from when this board was manufactured. So I'm going to use a smoke absorber fan when I work on this, so I don't have to inhale all this nasty stuff. So I managed to remove the original CPU chip without damaging any of the traces or pads. You can see that the traces are pretty fine, so if you have a pin that's still soldered in that hole and you go to pull that chip off the board, you're going to take that trace with it. And there are some pads that don't even have traces to hold them to the board, so they're also easy to remove. I used a combination of adjusting temperature on my tool and a little bit of liquid flux for some of the ones on the power rails and the ground plane. So I need to go back and I need to clean these holes out because we're going to need to solder a new chip in here. And then also I need to solder out the holes for the ROM chip because they're filled with solder. They got soldered closed through the wave soldering process at the factory when the board was made. I'm going to install my new 7810 processor. I have a stash of genuine new old stock processors. I'd avoid buying these, or for that matter any chips, off eBay or AliExpress or the like from overseas sellers, because odds are the part that you're going to get is going to be fake or black topped. Since this pin was a little tricky to remove, I'm going to install it into a socket. You may say, well, where would you get a socket for this 64 pin weird spidery package? And the answer is they're 2.54 millimeter pitch still. So I can take a row of headers here and a row of headers here and solder them in, and then do the same on the other side, like such. Well, I'll do it with my magnifying glass, but like such, and then I'll have a socket that I can install the chip into. So while I'm at it, I'm going to install a socket for my EEPROM chip. Before I put the soldering iron away and pop these chips in, I do need to reconfigure the mode 0 and mode 1 pins of the CPU to tell it to look for an external EEPROM. When it was running on the masked ROM, mode 1 was pulled up to 5 volts through a 4.7K resistor. That little guy there, R13. And the mode 0 pin was grounded. All we need to do to use the external EEPROM is to swap those two pins, mode 0 and mode 1. Mode 0 is on pin 29 and mode 1 is on pin 27. And being the professionals that they are there at Roland, they've made this nice and easy, no hacking up of the boards needed. There's some jumpers here. So right now you see there's a jumper installed here at J1, and in parentheses it has a little I for internal ROM. And what we're going to do is we're going to remove this. All we need to do is snip it off the board. And then we are going to install a jumper here at J2. In parentheses, it has a little E for external ROM. And just like before with the EEPROM socket, I'm going to need to clear these holes out because they are plugged up with solder from the original soldering process at the factory. There our jumpers are changed, and I'm ready to install the chips. So you can see I was kind of struggling with this CPU chip. It was very difficult to get the pins all in the socket without getting folded over on each other. I had to use the little tweezers, and it was stretching the limits of my failing eyesight. So it looks like now the chip is in the socket securely, firmly and securely. So let's get this board back into the synthesizer, hook everything up, and see if it works. Alright, let's get the power plug, and we'll have the moment of truth. Do we have a booting Juno 106? Looks like it. Looks like it, we do. I wouldn't expect any sound from this. Let's grab the audio and see if we have any sound. There's probably other issues. Yeah, there's no sound coming from this. But we have some of the buttons are working. Looks like not all of them are. Well, some of them are. Let's see. Yeah, the tact switches are in need of some help. But we are booting up, and we've solved the problem of the dead CPU. So this Juno has awoken from its slumber. Clearly there's more issues with it that need to be fixed, but that's beyond the scope of this video. I just wanted to show here how I'd go about troubleshooting a dead or locked up Juno 106, and how we can replace the mask ROM CPU chip with parts that can still be sourced today. The same problem that we were having with the CPU board, the main board, can happen with the processor on the module board as well. And the process to troubleshoot and repair it is the same as what we did here. I've got processor and EEPROM sets available on my website should you ever need them, or if you want to build a Juno 106 survival kit. I'm Synthchaser from synthchaser.com. Thanks for watching and have a great day.